This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio brings you relevant and detailed discussions about software engineering topics at least once a month. Thanks to our audience and the partners listed on our website for supporting the podcast.
So my name is Martin Laforest. I'm the manager of scientific outreach at the University of Waterloo and for the Institute for Quantum Computing.
Okay, so this answers my question whether I should pronounce your name English or French.
French if possible.
Okay.
But I got used to both of them, so it's fine.
Okay, how would I do it in English? Laforest?
Yeah, people say Martin Laforest.
Okay. Okay, so what's your group about? What are you doing there? Which institute are you working for?
So I'm working for the Institute for Quantum Computing. We are a very large institute, part of the University of Waterloo in Canada. So what we do here is we have about 100 researchers, and we have 17 faculty members right now, about 25 to 28 postdocs, and 85 undergraduate and graduate students. And what we do here is we're trying to harness the quantum world and understand how we can use it to perform quantum information processing. And one of the particularity of our institute is that we're trying to attack the problem from pretty much all the angle possible. So either from the implementation side with the physicists and the engineers that works in the lab or works on the theory of implementation, but also we have a lot of people, about half our researchers working on the computing side or the communication side, the very theory, very abstract way of understanding really what quantum resource can give us or how we can use quantum resource to do information processing. Okay. So we're really trying to tackle the problem from every angle and trying to understand really and what we can do with it and trying also to make it happen.
So this episode is primarily about quantum computing, but you already mentioned quantum information processing, and there are other terms like quantum communication and stuff. Can you maybe delineate those terms and explain what the differences are and what quantum computing specifically is?
Yes, absolutely. So quantum computing is really the science of using the quantum world, the quantum resource to do, as it says, computing, trying to make some computing tasks, solving some mathematical problem or other related problem that a classical computer might not be able to do or might take a long time to do. But this is one part of a larger field we call either quantum information processing or quantum information technology. And this englobes essentially anything that is related to information processing using quantum resource. It can be related to, for example, quantum cryptography, quantum communication. It can also go to quantum sensing, quantum actuators. But quantum computing is one subset of all those possibilities that we can do with the quantum world.
Okay. So I guess before we go into the somewhat of the details, what kind of high school physics do listeners have to know? I mean, we all probably know something about this quantum world, which is, quote, strange, where, probabilities rule and where nothing is like it seems.
Yeah.
So can you maybe give us a little bit of a quick, recap of the high school physics we need?
So in high school, a few people go in the core of what quantum mechanics is.
Okay, then let's say university physics.
Yeah. One of the little experiment that a lot of people see in high school, or at least in undergraduate studies, is the Young double slit experiment, which essentially demonstrate what quantum mechanics really is. So if people recall, the Young double slit experiment is shining a laser to two very tiny slits. And what we expect is if we shine the light through one slit, you get one blurb on the screen on the other side of the slit. If you shine the light to the other slit, you also have one blurb.
Right.
So what you would expect normally is if you shine the light through two double slit, you would get two blurb. But that's not what you get at all. You get an interference pattern with some bright spot and dark spot and bright spot and dark spot. Essentially, the way normally in high school you explain that is it shows the wave property of light.
Exactly, yeah.
Right? If you see light as a wave, then it will interfere. Then you can explain that the same way as, for example, a water wave would do the exact same thing going through two slits. But where it becomes particular is that you can also do that with just single photon at a time. So one particle of light, where you cannot have a smaller amount of light possible. So it's undivisible.
Yeah.
And if you consider that this way, you will still also see a pattern at the end on the screen. And the only way you can explain that pattern is if you model the whole thing as the photon going through the two slit at the same time. So you have one photon, you can pass through the two slit, and it essentially interfere with itself.
Okay.
And that shows very well one of the remarkable property of quantum mechanics that we call quantum superposition, which essentially says that a quantum particle or a quantum system can be in more than one state at the same time.
Mm-hmm.
So it's a superposition of state. And in this case, with the double slit, is the superposition of going through the right slit and the left slit at the same time.
I guess there is not much of a point of trying to like really understand this. It's just the way it is, right?
Essentially, yes. Quantum mechanics is, we can say, the ultimate laws of how nature works. So when you go down to the building blocks of nature, we're talking like molecules, electrons, protons, neutrons. At this point, the laws of classical mechanics, or essentially, the Newton laws or the laws of electromagnetism, from the Maxwell's equation, for example, they cannot explain how molecules behave or how electrons behave, for example. And that's where quantum mechanics come in. Mm-hmm. Essentially, it's a broader theory that really explains what happened when you go to the very small. Mm-hmm. Technically, it could also explain the way the word, like our word or microscopic word also work, but it's just those quantum effects are so small that in our everyday life, we don't really perceive them.
It's a little bit like a relativity. Every ball that falls from a tree has relativistic effects, but they're so small you can just as well use Newton. It's good enough.
Exactly. So the Newton's equation are an extremely precise approximation for a word.
Yeah.
But when you go to a little deeper of what nature is, it doesn't hold anymore.
Right. So which physical properties are quantified? I seem to remember spin, right?
Yeah, spin is an example of a quantum property that we don't really see on everyday life. But if you look at the spin, it's essentially just like a tiny spinning magnet. It has a magnetic dipole moment, but the only difference is that when you put it in a magnetic field, as long as you don't look at it, as long as you don't measure it, it can point along the magnetic field, against the magnetic field, or it can point in any direction. It can be in a superposition of pointing along or against. Once you look at it, unlike a classical dipolar moment, you will only measure it as either pointing along or pointing against. Mm-hmm. So here I'm talking about a spin 1/2. There's other type of spins, spin 1, spin 3/2, and so on. But a spin 1/2, for example, where when you measure it, will always either point along the magnetic field or against. Mm-hmm. So there's only two discrete states it can have.
Okay. Are there other quantum quantities or characteristics of atoms that are interesting for working in quantum computing or exploiting quantum effects in general?
You mentioned a lot of atoms and molecules, but that's not the only thing that shows quantum effect.
Right.
If you take, for example, one of the possible systems we investigate for quantum computing is a superconducting qubit that we call. Mm-hmm. And this is actually a fairly large system. It's about on the micrometer size. It's a nano-sized electrical circuit. But by adding in a few elements of superconducting material that we call Josephson junction, mm-hmm. then you can also start seeing some quantum effect. And one example, the one we call the flux qubit, you can have the current in your circuit either going around the loop clockwise or around the loop counterclockwise. Mm-hmm. But it can also be in a superposition of both clockwise and anti-clockwise.
Okay.
So that's another property, for example, we can use. So you mentioned spin. Spin is somewhat a natural candidate for doing quantum computing because it really has two discrete states. Mm-hmm. But at the end of the day, if you take any quantum system that has a certain property that has two discrete levels that can be accessed in a quantum mechanical way, this is potentially a candidate for a qubit. Okay. So I mentioned superconducting. You can think of an ion, for example, where it can be in the ground state or in an excited state. That could be your two state for your qubit. Mm-hmm. A photon is a great example. You can use a photon in many different ways to do a qubit. You can use polarization. A photon can be polarized vertically, can be polarized horizontally, but can also be polarized at any other angle.
Okay.
That can be seen as a superposition of horizontal and vertical.
Yeah.
Or the photon, you can also use what we call the spatial distribution of the photon, where we can take this photon through a beam splitter. It can go right or left. So you can call the right your 0 for a qubit or the left your 1 for the qubit. And that you can do that in a quantum way, which means that you can be in both the left and right fiber.
Okay.
Or you can use, again, with the photon, you can use a frequency. You have a center frequency. You can then your qubit can be either the frequency is a little higher or a little lower. Use that as your qubit. So there's many different ways. There's maybe out there more than a dozen proposals of different systems for building a qubit.
Mm-hmm. And of course, the qubit is the same thing as the bit in classical computing. It's the quantum bit that is basically the on-off or 0-1 state, although it can be in several states, which is the whole point of quantum computing.
This is the whole point, yeah. So at the end of the day, we still work with binary calculus. So it's still 0 and 1. That's still your answer you're going to get at the end. But by having a quantum bit, then you can have your 0 and 1 behaving quantum mechanically. So you can be in a superposition of 0 and 1.
Okay.
And here I see a lot of 0 and 1, and people might get confused of when we start doing probabilistic classical computing, where you can have a chance of being in 0 or a chance of being in 1, where the probability is any number between 0 and 1, right? Probability can only be a positive number. Mm-hmm. In quantum mechanics, that's where the beauty comes in. We don't work with probability, but we work with probability amplitude. And those probability amplitude can be any number on what we call the complex circle. So it can be a negative number, it can be a positive number, it can be an imaginary number, a complex number.
Okay, so let's get back a step.
Yes.
If we assume we would write classical programs with quantum computing, which we don't, and we'll get back to that. But then we could assume that a bit isn't just a simple 0 or 1, but rather, well, in the end it is a 0 or 1, but while we compute, it can be any value at the same time.
Yes, it can be put in any superposition you want, and that superposition, as I was saying, can take any value between any complex number value.
Yeah, and then once you measure, then the observation effect kicks in, and then it has to decide what it wants to be, kind of.
Exactly. So once you measure, you will only get probabilistically a 0 or a 1, and then that relates back to this probability amplitude thing, is that the probability of measuring either the 0 or the 1 will be equal to the modulus square of this probability amplitude. So at the end of the day, you still measure the answer with a certain probability.
Yeah.
But where the whole quantum mechanical things comes in is because we can have negative or complex probability amplitude, then later on in your computation, it can lead to interference. So it can lead, for example, to the probability of measuring 1 can interfere with itself and cancel out, so that at the end you can only measure 0. So that's a bit of a simplistic way of seeing things, but that's a little bit how it works. By accessing the quantum mechanical property of those qubits, then you have access to interference.
So the reason why I'm kind of emphasizing that is that I want to try to get to the point where it becomes clear that this is not the same as fuzzy logic, where you also have, instead of having zeros and ones, you have a continuum of basically real numbers between zeros and one, and you somehow calculate with not probabilities, but with analog values, if you will, 0 to 1, not 0 and 1. But this is different because the system can be in several states or maybe all states at the same time, which is not true for fuzzy logic.
That's absolutely right. I'm not entirely familiar with that fuzzy logic.
Me neither.
But yeah, at the end of the day, the only thing I can say is the main difference between probabilistic classical computing and quantum computing is that we don't only have access to positive number, but we have access to all possible number. And that what brings all the remarkable properties of quantum computing.
Okay. So, I mean, I'm a software developer, so I know how to write deterministic, well, they're not always deterministic, but I hope they're deterministic programs. And I know what to do with it and how this works. I mean, how can you do anything useful in an environment where kind of everything happens at the same time? So what do you do with quantum computing? And then, I mean, how do you tackle it? How do you actually make this do something useful?
I mean, this is a very hard question. And, building quantum algorithm, I have to admit, is not an easy science. It's extremely hard. You need to develop a very good intuition for quantum mechanics for it. But at the end of the day, to answer your question of how can we get the right answer if everything is probabilistic, is that we just need to be a little more clever. I'll give you a very naive picture, which is not the whole story, but you can see it this way. Well, let's say we try to compute a certain problem. We try to find the answer to a certain problem. Okay, so we know the algorithm to verify that the answer is true.
Right.
So what we can do, for example, we can use our quantum system and put it in all possible answer, and then you use the quantum algorithm to check if that answer is true. So now because your quantum system is an all possible answer, by applying that quantum algorithm, it's going to verify each possible answer and see if it's true. And what you can do is, if it turns out to be true, the quantum algorithm can essentially tag that little state. So at that point, your quantum computer is still in all the superposition of all the answer, but the one that gives you the right answer will be tagged. And then you can add an extra layer of algorithm to it so that only the answer that got tagged will have a probability of being measured and all the other one will just not be measured at all. So that's how you can transform a probabilistic algorithm into a more deterministic one. Okay. So this is one way of doing it, and that we call amplitude amplification. So you amplify the amplitude of measuring the right answer. This is not the only way. There's also other ways of doing it by computing more using the phase of the states, and that's really when you start tackling the quantum mechanic a lot. Because you work with probability amplitude, and I say those amplitude can be any complex number, you can sort of encode all your information in the phase of the state, and then again use a very clever algorithm to and then to make all the wrong answer interfere and not give you any probability of measuring, and then all the right answer to interfere constructively so that they will be measured at the end. And I say again, this is a very naive way of saying things. Things are much more complex in real life, but that sort of gives the idea of how it can work.
Right. So if you say we amplify the amplitude and we mark something and things like that, this is all physical interactions. This is not a program in that sense that you write in some particular quantum programming language, right? This is all hardware, if you will.
Well, at the end of the day, right, if you look what a computer language is just a shortcut to tell your computer what to do.
Yes, right.
Right. At the end of the day, the computer, what it does is it take the bit and then it flip them and then make them interact with another bit. But when you use a language like C or Python, it's just a quick shortcut that when you say multiply, then it knows that it has to do to implement in the processor the multiplication algorithm. So in quantum computing is essentially the same thing, but we're just not at the point of having a high-level programming language yet. I mean, some people do program some sort of a compiler or language, but at the end of the day, it's really a shortcut that tells your electronics to do something. And that something is either, flip a bit, make that bit interact with the other qubit, and then that qubit, measure that qubit, and according to the measurement, do something else. So at the end of the day, it's very hardware. You still need to go control your bit.
Yeah, but you're right. I mean,
qubits,
it's it's not that different from having a transistor, that does something on a chip, and then having another transistor that does something with the output from the first transistor and stuff. It's just that this is all so highly integrated these days that you don't notice this, and you actually kind of have a programming language.
Yeah, exactly. So now, you put it very well. So nowadays, it's so well integrated, we don't even think what's going on in the processor. But if you go back in the early days of the computer, that's what they were doing. They were telling the computer, back then it was a vacuum tube. So they were directly telling each vacuum tube, okay, you're going to switch a signal on that side or switch a signal on the other side, and then, really step by step. So we're essentially there right now in quantum computing. We still work on the, on the machine language.
Yeah.
We directly tell the qubits what to do.
And also, staying in the analogy, you don't even know that it's going to be transistors in the sense that you are still experimenting with different physical representations of qubits.
Yes, absolutely. As I was saying before, there's about a dozen, probably more than a dozen proposals. All of them have some very good points, and most of them also have some bad parts. So we haven't found the Holy Grail of the qubit yet.
Yeah.
So that's why we're, different people work on different technologies, but some people working with photons, some people working with superconductors, semiconductors, ion trap, you name it. So there's not one consensus yet of what the quantum computer will actually look like at the end of the day.
Right.
That's why we do research. We're still trying to either find the Holy Grail or just use what we know now and improve it, and then at the end trying to make it behave the way we want. Because that's the problem with quantum mechanics. It is stubbornly classical. It doesn't like to stay quantum mechanical.
Okay.
And by that, what I say is that this famous quantum superposition I'm talking about, it's an extremely fragile state. So once you have a system in a quantum superposition, it or any quantum system tend to interact with its environment. it's very similar as if the environment was actually reading the state.
Right.
And by reading the state, then it brings it from a quantum superposition into a classical statistical mixture. So you go from the quantum to just a probabilistic bit. And most of the effort nowadays, and pretty much all the system, is to beat that interaction with the environment that we call decoherence. So we're trying to better isolate our system from the environment.
Right.
But you cannot completely isolate your system from the environment, because at the end of the day, you need to manipulate your system.
Yeah, exactly.
So you need to couple to it. So it's a bit of a catch-22.
So in some sense, what you want to do is you kind of want to insert the problem, and then you want it to be completely isolated. And then once it's finished, however you know this, then you want to put in a probe to measure the result, kind of.
Well, this is a measurement, yes. But to do to implement an algorithm or to just control your system, you need an external system to control it. I'll just take, for example, we were talking about spin. Spin is a fantastic candidate for a qubit because it only has 2 levels. Normally, it's somewhat very well isolated from the environment. But if you want to control them, then you need to use microwave or radio wave. So you need to couple an external system to your isolated system to control it. Mm-hmm. So even though it's isolated very well, you still need to unisolate it to control it. And that's one of the large challenges. How can you control it without disturbing it too much or without making it interact with things that you don't have control over, i.e. what we call the environment? Mm-hmm. So that's one of the main challenges nowadays. And then you mentioned also, at the end of the day, you want to measure your result. That's also a challenge. And some technologies are very good at measuring. Some of them are not very good. So as I was saying, all technologies have their good point and that they have their bad point.
Yeah. Is it expected that there will be one common standardized representation of a qubit like the transistor in classical computing? Or do you think, of course we don't know, but what's the community opinion, that will there be different representations for different tasks or kinds of problems?
Well, one thing that people seems to go toward is that we're most likely going to be moving toward a hybrid quantum computer. And by that, what I mean is you might have some sort of processor that might work with either a spin or an ion or you name it to do your computation. But then if you want to send your information or your quantum information or send your quantum answer somewhere else, you might have to couple it to what we call a flying qubit. So a qubit that can actually transport that information, which, at the end of the day might most likely be a photon. Yep. No, I'm not saying that with 100% certainty, but the photons are great because they travel at the speed of light because they are light. And they tend to interact very little with their environment. So once you've been able to put your quantum information in a photon, you can send it down a fiber or free space at the speed of light without losing too much of your quantumness in your information. Yeah. But this is one way. At the end of the day, to answer more clearly your question, I don't think there's a consensus yet. Okay. Because if there was a consensus, then everybody will be researching on the same system. Yeah. Right. So everybody researching their own system believe it might be the system or it should be the system. Yeah. Another consensus that seems to be arising more and more nowadays is we try to use existing technologies and push them to the quantum limits to do quantum computation. I'll just come back to the example of superconducting qubit. Mm-hmm. Right? A superconducting qubit is made with capacitor, with inductors, with resistors, and with those Josephson junctions. So that's this extra little tool that we add of superconductors. Mm-hmm. But at the end of the day, everything is built on a chip with existing current technology for doing, example, E-beam lithography or atomic layer deposition. So we can use all the technology being developed in the name of classical computing by the chip builder companies who became extremely good at doing very small scale pattern on the chip. So we're trying to essentially leverage that knowledge or that expertise and then use that and then push it to the quantum limit. Yeah. Superconductor was one example, or you can think also of building quantum dots on semiconductors, right? The entire computer industry became extremely aware how to work with semiconductors. So here we're trying to use it and then push it to the quantum limit.
So let's take a look at how a quantum computer today looks. I assume these are still rather big machines. I've seen photographs, with lasers and colorful lights and big metal thingies. So can you explain, obviously, as you say, there are several, but can you pick an example of like the physical components that go into such a machine, how it looks and how it works?
Sure. Maybe the example I can take is nuclear magnetic resonance.
Okay.
In nuclear magnetic resonance, we use the spin of the nuclei in an ensemble of molecules to do quantum computation. So we know nowadays that we will never be able to build a quantum computer with nuclear magnetic resonance because, first of all, we don't control single molecules, but an ensemble of molecules.
Yeah.
And that leads to a whole other set of problems. So at the end of the day, the scalability of that system is jeopardized because it has very little polarization, but we're getting a little technical.
Okay.
To explain how this look in the lab is, so first of all, to have the spin, in order to separate the two states, and so in order to have a separation between this, what we call a spin up or a spin down,
right, yep.
So spin pointing along a magnetic field or against a magnetic field, well, you need a magnetic field. Mm-hmm. And for nuclear magnetic resonance, you need very large magnetic field of order of 1 to 10, 20 Tesla. So you have a very big can that looks like a beer keg. It can be all the way up to a couple meters in diameter, maybe even bigger, to a couple meters, 3 meters high. Mm-hmm. So that can be very large. But this is really just to have a really big superconducting magnet. For example, one we have here is we have a 15.3 Tesla magnet, which is 200,000 times bigger than the magnetic field of the Earth. So you don't want to have your credit card on you when you get close to it.
Yes.
So this is really just to put your ensemble of molecule in the middle of the magnet, and that's to provide that energy separation between being pointing along the magnetic field or against.
Okay.
So it will take less energy to point along and more energy to point against, because at the end of the day, nature is lazy. It always likes to be in a low energy state. The spin will naturally point along the magnetic field. So that would be to initialize your computer, for example. But now you want to make your qubit perform operations. So you need to control them. You need to go from a spin up to a superposition of spin up and down. And that for doing this, we use radio wave. So that's where the whole resonance come in for nuclear magnetic resonance. And essentially the idea of this, the way it works, is rather simple. You can think about it as when you were in grade school in the merry-go-round. So you were turning around the merry-go-round. And then this is what a spin does when you put it in a magnetic field in a superposition. So if you put a spin in a superposition in a magnetic field, it precesses around the magnetic field at quite high value. They make, depending on the size of the magnet, they can go several hundred million turns a second.
Okay.
Wow. So we're working with hundreds of megahertz. Mm-hmm. Now, if you want to make them flip or make them spin, what we use is a rotating magnetic field. So I'm going back to my merry-go-round example. Let's say you're on the merry-go-round and you're spinning around and you're trying to talk to your friend on the ground. Then it would be very hard to talk because you can really only talk when the spinning guy arrives close. Right. But then when it goes away, you cannot talk anymore because you can hear each other. Mm-hmm. But if your friends start running around at the same frequency as the merry-go-round, then you can, as far as you're concerned, your friend is just right beside you and never moves, so you can have a conversation. Your friend would be out of breath, but you can still talk. No problem. So that's essentially what we do here is by sending a magnetic field pointing in a certain direction, but also rotating at the same frequency as the spin. As far as the spin is concerned, it sees a certain magnetic field in a constant direction and start rotating around it. And that's how the whole radio wave comes in, because a radio wave is essentially a rotating magnetic field. Well, when you connect a radio wave to an inductor, then it creates a oscillating magnetic field. Yeah. And then that approximates very well to a rotating magnetic field. So this way, by having this oscillating magnetic field at the same frequency as your precession of your spin, then you can start making them rotate about any angle you want. So that is for creating what we call single qubit operation. So you can control single spin this way.
So basically you can set a qubit to a certain value, if you will.
Well, to a certain superposition.
Superposition of values, yeah.
Yes.
Okay.
And here I mentioned NMR, but if you work with spin in a quantum dot, it's the exact same principle. And then we became so good in NMR at controlling this, like we can create the exact superposition we want with a precision of 99.9995%.
Wow, okay.
So NMR in terms of control is very good. So as I was saying, we know that NMR is sort of jeopardized in terms of scalability.
Yep.
It's a fantastic testbed because it is a working prototype of a quantum computer. So we can develop techniques in this system that can later on be applied to different systems that use the same sort of dynamics or also use spin.
Okay. So, but at this point, we just put values in, right? There hasn't been any calculation or operation yet.
Well, this thing of rotating the spin is an operation. Example, if you do a rotation of 180 degrees, then you took your spin up into a spin down. So you essentially did a NOT gate. You turn a 0 into a 1. Or if you just do a 90-degree rotation, then you turn your 0 into a superposition, an equal superposition of 0 and 1. And this is an operation that is extremely critical in quantum computing that we call the Hadamard operation, which creates a superposition of 0 and 1 out of a classical state of 0 or 1.
Okay.
But so far, I only mentioned the radio wave for controlling a single qubit. But if we have a molecule with several different nuclei in it, let's say we have 3 different nuclei that we can control. So using radio wave right now, it only gives us 3 1-qubit processor. You need to make them interact with each other because, you can just control 1 qubit, but if you don't make it interact with another qubit, then you don't have a 2-qubit system. Right. You just have 2 1-qubit systems.
Absolutely, yeah.
Actually, nature has been nice enough where in the spin example that they naturally interact with each other. So if you just let them go, they will interact and then they will create what we call entanglement.
Okay, that's another one of these quantum effects, right?
That's another one of these quantum effects that we can come back a little later. It's even more remarkable than the superposition, in my belief.
Okay.
But essentially, we need entanglement to really use all the power of quantum computing. And then in terms of spin system, it occurs naturally. It's by letting them evolve, they will naturally interact with each other. So we need to time the amount of time they will interact to make a certain operation.
Okay.
So at the end of the day, what I'm saying is that we need extremely precise radio wave generator, and we need an extremely precise timing. And one of the very nice little trivia about, for example, nuclear magnetic resonance spectrometer is that the technology used for the timing is the exact same technology we use in GPS, the same type of clock.
Right.
So extremely precise clock, and they come for cheap because GPS is well spread now.
Yep.
Well, yeah. So this is one example of one system, the type of infrastructure that we use. The big magnetic field, radio wave, timing, but that this is just the very simple way of seeing it. If you see the big machine, there's a lot more electronics involved in it.
Yeah. And so we use the radio waves to put stuff in. How do we get stuff out? How do we find out the resulting superposition? So
this is highly, highly dependent on your system. In NMR, for example, to read out, as I was saying, because we have a spin is it looks like a tiny magnet. Yep. So when it's in a certain superposition, it will rotate around the magnetic field. So because it's a rotating magnetic field, it will create a rotating electric field. Okay. That's one of the laws of electromagnetism. So you can think of putting your system in an inductor or like a coil, a solenoidal coil. And then because their spin turn around, it will create a changing magnetic field, which in turn would create a changing current in your electrical circuit. And then you can just plug that in an oscilloscope and then read the frequency at which your spin rotates. And from that, you can deduce the state of all the other spin in your molecule. That's one example.
So basically the way a quantum computer works is as follows. You have this physical/mechanical equipment. You start up the system. You use your input facility, in this case, the radiation, to put your quantum thingies, whatever you use, into a specific state or superposition of states. Then you have them interact. You wait for a little while because the time you give them for the interaction determines how they interact. And then you measure the resulting superpositions/spins in this case.
Yes and no. This is maybe a little too simplistic. At the end of the day, a quantum computer will work essentially just like a regular computer. So you need to find a way to initialize your system. So, for example, when you start up your computer, you know all your system is booted up. You know exactly what state it is.
Right.
And then you want to do a certain task. So you have an algorithm. And an algorithm is always broken up in terms of smaller operation. Apply this type of operation to the first qubit, this type of operation to the third qubit, and then make the third and fourth qubit interact. And then so it's a series of operation. So this is the quantum algorithm. When you get into the physical process, then you need to translate all those operations into physical operation to relate to what I was talking. Like, for example, if you have a single qubit operation, then it will be some radio wave. And then if you have 2 qubit operation, so in an interaction between qubit 1 and qubit 4, then you will have you will let your system evolve for a certain time. and then you will have other single qubit operation, and then another 2 qubit or 3 qubit operation. So it's always a series of different operation that we do physically in the lab. So there's always a need for translating the actual algorithm that they give you step by step what to do into a physical action of what we're going to do, like when we turn off the radio wave generator and when we let the system evolve freely and so on.
Right.
But what we're explaining here is what we call the circuit model. It's very based just like the classical computing, where you have certain bit and then you do certain operation linearly or in parallel and so on. But that's only one type of model for computing. There's other proposal over there. One of them that is becoming more and more studied is what we call the measurement-based quantum computer. And the one this way work is you start with your system in a special state that we call a cluster state. Mm-hmm. And then the way you do computing is just by measuring different qubits in different way. And depending on the answer, then you change the type of measurement you do later on. And that's how you create your computation. Okay. Not by actively controlling your qubit, but by actively measuring them. That's another model. Another model out there also, it's called the adiabatic quantum computer, which is, I'm personally not necessarily an expert in it, but the way it works is essentially your algorithm is translated into a certain dynamics of your system. And by slowly changing the dynamic of your system toward what you want, your quantum system will always remain in the state of low energy. And that state at the end of the day gives you the answer. That's another type. So there's not only one way of doing computing, but there's different proposal out there depending on the system. So some systems are more suitable for the measurement base, some systems are more suitable for the circuit base, other systems are more suitable for adiabatic. So at the end of the day, quantum computing, there's many possible ways, many different systems, and then there's research being done in all of those because
still early days.
It's still the early days, and we still don't know which one's going to win the race.
Right. You mentioned entanglement, and as something you wanted to come back to because it's fascinating. What's entanglement?
Yes, it is fascinating. It's one of probably the most counterintuitive property of quantum mechanics.
That's good, because we didn't have any counterintuitive stuff yet, so great that we have something counterintuitive. So go on.
Well, the superposition thing is quite counterintuitive. So let's go even more counterintuitive. So the whole superposition, quantum superposition, was when one quantum system can be in multiple states at the same time. Mm-hmm. Now take two quantum systems. And then you can put them in superposition also, but you can put them in such a superposition that your two qubits or your two quantum system are extremely correlated, more correlated than you can ever explain it using just classical physics or classical correlation. And one of a particular example I can say, let's go into a little bit of details, but it should not be too hard.
Okay.
Let's take two photons, okay? So as I was saying, you can use, as a qubit, you can use a polarization of the photon.
Yep.
So you can call your 0 a photon having a vertical polarization.
Right.
And you can call your 1 horizontal. Mm-hmm. So now if you look at a photon with a polarization at 45 degrees, then this is a superposition of horizontal and vertical. Yep. Just like, basic Cartesian coordinates, right? Yep. If you take two entangled photons, if we entangle them in a special entangled state, what's going to happen is if you measure one qubit in the vertical polarization or the horizontal, if you measure it in the vertical horizontal basis, once you measure one photon, you will know right away what was the value of the other photon. So if the first photon gives you a horizontal, you know the other one was in the horizontal. If it gives you a vertical, you know the other one would be a vertical.
Okay.
So this is not surprising yet. You can just have two photons that are either horizontal or either vertical that will give you this correlation. Where the whole quantum entanglement comes in, and that special entangled state, is now, if you look in the other basis, if you measure your photon in the 45 or minus 45 degree, if it's a classical state, measuring the state of one photon will give you a half and half probability of being either vertical or horizontal. But then measuring the other photon will also give you a half or half probability. So they're not correlated anymore. Mm-hmm. They were correlated in one basis, but not on the other basis. But that special quantum state, that entangles quantum state, that we call also the EPR state for Einstein, Podolsky, and Rosen, the people who raised that weirdness of quantum mechanics back in the days. Mm-hmm. If you take that state and you measure in the 45-degree basis, then you will also know immediately what the other one state is. So essentially, at the end of the day, what I'm saying is like no matter in which angle you measure your photon, it will always be correlated with the other photon also. And this is something that classical mechanics cannot explain.
Mm-hmm.
And that is something inherent to quantum mechanics, and that's what we call quantum entanglement. So it's essentially just like your two quantum system were behaving as if it was only one system. They're completely correlated. They dance together all the time, no matter which way you look at it.
Okay. And it's currently, as far as I understand that, unclear how they exchange the information, if you will.
Yes, it's unclear. Some people take the very pragmatic way, essentially like just people like me who just say, this is how it happened.
Sure, yes.
And then we're happy with it.
Yeah.
But there's also a whole load of people out there trying to understand what is going on. Some people just say, no, it cannot just happen instantaneously. There's something missing there.
Yeah.
And then that brings the whole researcher on the foundation of quantum mechanics, trying to really understand what is going on, which is, at this point, it's more of a philosophical question than a practical question. So as far as I'm personally concerned, that's how quantum mechanics is described. That's how it works in the lab. I'm happy with it, and we just try to harness it and then make some very neat stuff with it.
Actually, this is a very good segue, making some very neat stuff with it. We should talk a little bit about what you do with this stuff. So maybe to, again, look at a last kind of theoretical aspect. In classical computing, there is the Turing machine.
Yes.
This is basically something that says what kind of ingredients you need to be able to calculate everything. Well, it's very simplified.
Yeah.
So, and it's a way of characterizing something as being a Turing-complete computer or not.
Yes.
Is there something similar for quantum computers? Is there a quantum Turing machine? I mean, a kind of criterion you say, this is a complete quantum computer. It can calculate everything that you can do with quantum computing.
Yes. Essentially, there is such a thing. So, at the basis, at least my version, the way I understand the Turing machine is that if you have a Turing-complete computer, then you can simulate any other type of Turing-complete computer with just a polynomial overhead. So essentially what it says is all computers are equivalent.
Yep.
If there's a problem that is really hard to solve on one computer, it would not be easy on another computer. It will also be hard.
Yep.
So, but this is all based on classical computing when you only have bit. And when you toss in quantum resource on top of it, then the Church-Turing thesis doesn't hold anymore. Because we know there are some problems that we can solve on a quantum computer more efficiently than on a classical computer. So it sort of shattered the whole Church-Turing thesis.
Okay.
But there is an equivalent saying that if you have anything that is computable on a quantum computer will also be computable on another quantum computer. So the bottom line is Church-Turing thesis does not apply to quantum computing, or let's say quantum computing breaks the Church-Turing thesis, but we have also the equivalent saying that a universal quantum computer will essentially at the end of the day be all the same, because that's what we want to look for, right? Something that is universal, something that can do any possible computation. And at the end of the day, quantum computing is a generalization of computing. So any quantum computer is able to simulate a classical computer.
Okay.
A classical computer can also simulate a quantum computer, but it simulates it with what we call an exponential overhead. So it means it takes an exponential amount of operation in the number of qubits to simulate a quantum computer.
Mm-hmm. Okay.
Somewhat the quantum equivalent of the Church-Turing thesis says that any quantum computer will efficiently simulate any other quantum computer.
Right. And this is, again, the same polynomial efficiently thing going on.
Polynomial efficiency and all this, yes.
Yeah, okay.
But this now you're taking me a little bit outside my comfort zone. I'm a physicist.
Okay.
I know a little bit on the computing side, but we've talked a lot on the implementation of quantum computer, but there's a lot of effort being done by the computer scientists and the mathematician and the theoretical physicists to understand how much advantage does the quantum resource give us. We know it gives us advantage, that's for sure. We know that it's more powerful. We know it has a very high potential, but we still don't know really how much.
Yeah. So do we know in which areas it has advantages? I mean, getting into the application slowly, what would we do with a quantum computer that we cannot easily or efficiently do with a classical computer? Are there any examples today, or are there any expected examples? I mean, what people always say is once we have quantum computing, we can break today's crypto systems.
Yeah, that's probably we use it a lot as an example, because I mean, I'll be honest. This is not the goal of doing research. We don't want to just go around and crack every credit card out there. That's not the goal.
So
But
you don't work for the NSA then, I guess.
no. Maybe some people out there.
Sure
That's
they
their
are.
goal. But the factoring algorithm, this is the perfect example that shows how much of an advantage it can give us. But the slight little thing with the factoring algorithm is we're not sure yet that it is inherently stronger. And what I mean by that is, let's say you multiply two n-bit number together, that gives you about an n-square bit number.
Yep.
And then if you want to do the other way around, it's extremely hard. So it will take an exponential amount in n to factorize that number. But it hasn't been proven yet that there exists no classical algorithm to do it. We just don't know it, but it hasn't been proven that there's none existing out there.
Okay.
The only thing is that we know there exists a quantum algorithm that can factor numbers using only a polynomial amount of operation. So this does not provably show that quantum computer is stronger, but this is a very strong contender on showing the power of it.
Yeah. So how would that work? I mean, roughly?
Well, the way it works is, the algorithm is called the Shor algorithm because of Peter Shor, who came up with it.
Mm-hmm.
Back then, he was working in, I think, Bell Labs, and now he works at MIT.
Okay.
So he developed this algorithm back in '94. And I will not go to the details of how it worked because it's extremely complex.
Okay.
But if we go to modulo calculus, which is essentially like the clock.
Yep.
You talk modulo 12, so every time you hit 12, you start back at 0 and so on.
Right.
So he started with the premises that you can modify the problem of finding the factor into finding the period of a certain number in modulo calculus. And that period, it means like how many times you need to multiply the number with itself so that it's equal to 1 in a certain modulo calculus. So he changed the problem to this problem, which are equivalent. And he has shown that you can efficiently find, using a quantum computer, the period of the numbers, which you cannot do using a classical computer, or that at least we don't know how to do yet.
Okay.
The only algorithm we know takes an exponential amount. So you just change the problem to a different problem that is related, and then show that a quantum computer can find the answer you're looking for in a polynomial amount of time.
Okay.
So, and I don't want to go to the detail of it because we need a blackboard and lots of chalk.
Good. Okay. Other examples of what quantum computers are supposed to be able to do once they kind of work in the real world?
Oh yeah, there's tons and tons of them. Probably one of the first applications we will have is to simulate quantum system. Because as I was saying a little before, we can simulate system on the classical computer, but every time you add an additional system or an additional degree of freedom, it will always take an exponential amount more computing power to deal with it. But using a quantum computer, it's kind of intuitive that if you have a computer that works on quantum principle, that you will be able to simulate other quantum systems.
Yeah, it doesn't sound like a very big surprise to me, I have to say.
Exactly. So that's a whole field of quantum simulation. The potential of this is that if you can really simulate a quantum system of all the nitty-gritty of that quantum system, you can start really looking at how molecules interact with each other, or, for example, how crystals of certain material form and how the electrons interact within it.
So that's where the real world kind of connection comes in.
Yes, and then what that can lead at is, for example, exploring new materials. One of the very interesting applications is that we could be able to simulate how crystals behave and investigate superconductivity, for example. Superconductivity is a very bizarre behavior of certain material that is somewhat understood using the BCS theory. It's well understood, but it's very hard to completely simulate how it works because it takes so much computing power to do it. So at the end of the day, the only thing we can do is use approximation. Mm-hmm. And those approximation, as they say, well, they only approximate, they don't give you the whole thing. So now imagine you can really simulate exactly the way molecules and the aggregates of atoms interact with each other. Then you can really start understanding this whole phenomenon of superconductivity and start engineering or designing materials that will show superconductivity at higher temperature than now. Because now you have superconductor that can go maybe at 100, I think it's 100 Kelvin, somewhere around that. So it's still very cold. It's not very useful for everyday application. But if you could really grasp the idea of superconducting, using quantum simulation, then you can really start investigating, okay, how can we get a material that would be superconductor at room temperature?
Right.
And that would have a fantastic application, either just for electricity transport, so there's no more electrical loss. Just imagine building electronics. If your electronics is built using superconductor instead of copper wires or other resistive elements, then there's no need for cooling down anymore.
Yeah.
Another example is you can start looking at how the molecules would interact with each other, and that would be fantastic for designing drugs.
Yeah.
Instead of designing drugs the way we do now with lots of approximation, lots of empirical results, or not precise, you can really start looking how molecules interact with each other, and then design the drug the way they should be.
I was going to say that these are all very special kinds of problems, but I guess that's because I'm biased. I mean, the kinds of problems we use our computers today are also special in some way, in that they can be efficiently implemented with today's computers. So is it fair to say that quantum computers will not replace traditional computing, but will be more like let's say a coprocessor, or a 3D card that can do certain kinds of calculations or simulations especially well?
I'm always hesitant to answer this question because I don't want to be the guy who gets quoted in the future saying something stupid.
Yeah.
Just imagine the person who developed the laser 50 years ago. Right? I mean, that was just a cool little trick he was doing with lights. He never thought it will turn out to play music on a CD player or doing eye surgery. Right?
Yeah, absolutely.
But I think one thing that is safe to say is we know a quantum computer can do everything a classical computer can do.
Mm-hmm.
I mean, I don't think it would be far-fetched to think that maybe at the in 50 years, 100 years, I don't know, maybe every computer would be a quantum computer. But it's just that the task that the classical computer would be bad at doing, then the quantum computer would be able to do it. But where is that going to bring us at the end of the day? I have no idea.
Sure.
Well, we have idea. We know where it's going to go, but there's a whole other possibility that we probably don't even think of that people will come up with in the future. So we know for a fact that using quantum technologies or using quantum behavior to build technologies is the next technological revolution that we're convinced of.
Mm-hmm.
It just opened a whole different dimension of what you can do in terms of task, in terms of so now here we talked about computing, but computing is it's one subset of things we can do.
Right.
We can use a quantum world to do sensing, for example. I was saying that quantum world interacts a lot with the environment, and it's very hard to stay quantum. Well, then you can use that at your advantage to do much more precise measurement or much more sensitive measurement or sensing. This field of quantum sensing, now that we're there, is actually a reality right now.
Okay.
This has immediate application in the very near future. Like the quantum computer is sort of the holy grail of what we're looking for down the road.
Yeah, because it's the most general kind of device.
It's the most general. It's going to be the biggest one. It's going to be like once we have a quantum computer, we can say that we won the victory over the quantum world. We understand, can control it, can harness it.
Right.
But in the meantime, there's a lot and lots of discovery that are being done. There's fundamental discovery, just understanding how the world actually behave at the quantum level. But there's also small other little, I call them the quantum gizmos, little toys that you build in the goal of the Holy Grail, but that in the meantime can be used for other tasks.
Example, yes.
One of our researcher, actually newest member at the IQC, Dr. David Corey, he works a lot on quantum sensor and on immediate application of what you can do with quantum information processing. And he developed, not so long ago, using ideas developed for quantum information processing, a much more sensitive sensor for oil exploration.
Mm-hmm.
Who would have thought that building a quantum computer will lead to sensors for oil exploration?
Right.
Right now, he's also devising small little detectors to be able to detect the amount of sugar in the blood that would be non-invasive. So you would not have to to get a sample of blood to do it, but it will be able just to sense it at the surface.
Interesting.
Another thing he did, which was quite a big achievement, is he applied ideas that he developed for quantum information processing to neutron interferometry. So he works with the National Institute for Standard Technology in the States, and they have a neutron interferometer that is used normally to image crystals or image material to very small resolution.
Yep.
But the problem with those is that they're not very robust. They're very sensitive. They stop working very easily. And by applying ideas that we develop in quantum information processing. He's been able to improve the factor of merit of the neutron interferometry by a factor of 600.
Okay.
People kill to have an increase of a factor of 2. And by applying what we develop in the name of quantum computing, he's been able to increase that by a factor of 600. So those are an example of immediate application of what we do.
Cool.
Other applications, something we haven't talked at all yet, is quantum cryptography.
Okay.
So by doing a cryptography protocol, namely key distribution, how to exchange a secret key between two parties, you can use the quantum state of photons, for example, to do that. So that if there's somebody in between trying to steal your information or trying to listen, then you will detect the person.
Right.
So the eavesdropper would be detected. Right. And this is an actual reality right now. There are companies out there that actually have a commercial product that you can buy. There has been, I think it's the 2006 Swiss election. The ballots were transmitted using quantum cryptography.
Really? Wow.
Yes, it was. It was done in Switzerland.
Okay.
So there's about, out of memory, 4 or 5 commercial products out there that you can buy that is a quantum cryptographic protocol.
Okay, wow. It's also useful that you can get, concrete benefits from intermediate steps to the quantum computer and not just, like the fusion guys who work for, it's always 50 years away and all the intermediate results there might be progress towards fusion, but you can't do anything with these intermediate results.
Well, I'm surely convinced that the people working in fusion have some intermediate steps. It can be as simple as developing a new type of detector.
Oh, sure. I mean, in that way, yes, sure. But
like there's a lot of example of some groups around the world that were working on superconducting qubit, and then they find out that. But even actually, it happened here also in Waterloo. Sometimes the equipment you can buy off the shelf is just not good enough. Yep. It's not fast enough, or it's not precise enough. So we just build our own. And then from that, you make the technology advance. So those are sort of the side result that they are always welcome. Yeah. But yes, as you were saying, a lot of step, we do fundamental research. We're still at the point of understanding the quantum world.
Right.
And by understanding more and more, you can see more and more of the possible application you can do. And then along the way of working in that very big project that may take 20, 30 years, we don't know. Hopefully not as much, but, but in the meantime, there's a lot of product coming out, and then you will see a lot of technology working solely on quantum principle showing up more and more in the very near future, I think.
So is that the kind of time frame you have in mind, 20, 30, 40, 50 years until we have a quantum computer that is, should be called a quantum computer?
It's very hard to say.
I know, sure. But
I would tell you it's probably not for the next 5 years.
Yeah, sure.
But, at the end of the day, you never know what can happen. I'll just take, the classical computer as we know it today. Have the transistor never been discovered, we will probably never have a computer. Just all of a sudden, somebody discovered a transistor, and it was like a massive leap in the development of computer. Maybe that's going to happen also in quantum computing. Mm-hmm. Maybe not. Like, we don't rely only on it. We do a lot of effort. We work very hard. But one thing is for sure is the state of the understanding and the controlling of the quantum world compared to what it was 10 years ago has made a tremendous amount of progress in the past 10 years. It's quite impressive what we can do now with quantum system.
One of the last questions I had here was, do we already know how a programming language or algorithms for quantum computing would look like? Would they be relatively similar in the sense that you would still have a procedural program, but the single operations are quantum operations, or would they be inherently different or parallel? Or is there anything we can say about that in a way that I understand it?
I think it's fair to say that's once you have a quantum processor that works the way you want, then it's fair to say that you might have at some point a high-level language. It comes back to exactly what I was telling at the very beginning.
Yep.
A language is just a shortcut for operation being done physically. We do already use some sort of higher-level programming. You can. I'll take, for example, this Hadamard gate that I was talking previously, the one that brings a 0 into a superposition of 0 and 1.
Yep.
Well, depending on the technology, sometimes this Hadamard gate requires 3 or 4 different type of radio wave pulse or microwave pulse. So you can either tell your system to say, okay, do this pulse and that pulse and that pulse and that pulse.
Yeah, sure.
Or you can just regroup that into one pulse that you call Hadamard. Sure. That then you translate that and then you just tell your machine to do the 4 of them. I think it's fair to say that as we move along and then we start doing more and more complex operation on our quantum system, that the higher level language will start showing up.
So what I was trying to get at was, if we look at systems today, there are different paradigms like event-based reaction, reactive systems, sequential systems. There are different paradigms. There are different ways of describing data, like zeros and ones or kind of fuzzy stuff. So I was trying to find out whether we already have a feeling for what would be a good programming abstraction or a good, paradigm of addressing or working with the quantum world.
Okay, I see your point. Well, I already mentioned a little bit the different paradigm that we have right now. There's the circuit base, there's the measurement base, and there's the adiabatic base. Which one's going to win the race? I don't know. But each of them are more suitable for a certain specific system. The circuit base is very well suited for spin-based quantum processor because, you have one spin is your one qubit, the other spin is your other qubit. So you have distinct qubit, and then you can make them interact and then make them do single operations. So the circuit model works very well for those. But if you take the measurement base, for example, it's fair to say that this one is very well applicable for photons. Because photons, one of the very good things with photons is they don't interact with each other. So it means that they don't decohere easily. But one of the very bad things with photons is that they don't interact with each other. So what you can do, the part with the measurement base, is that you start with a very large entangled state. In quantum mechanics, interaction with each other and entanglement is similar, is the same thing. When you have two quantum systems interacting, they will most likely end up entangled. So you can prepare your photon a priori. So at the beginning of your computation, you prepare there in a certain state, which might be hard, but at least you can repeat it as often as you need. But then when you have your state, then you can do your computation by just measuring it. So you bring all the complexity of your problem at the very beginning. And then once you want to do your computation, you just detect the photons. And that's something that we're becoming increasingly good at detecting photons. Yeah. So where I'm going at is that there is different paradigm, but it will be hard to say which one is winning the race right now.
Yeah.
We're too much at the infancy of the field.
It's really interesting one really has to be careful. I have to be careful to not be spoiled by the fact that we are so used to classical computing, because when you say prepare the photon and measure, this sounds all like big machinery to me. But today, of course, or back then when we built the first classical computers, we also prepared some electrical charge in some, pit somewhere, and then you started the computation. So it's quite analogous. It's just that it's much earlier days.
We're still in the earlier days, yeah. I mean, that's why I always refrain from trying to reach any conclusion.
Right, I agree.
Because, I always mention this quote. I don't remember exactly who said it, but when they were talking about the very first computer, the ENIAC.
Yeah.
And then they were saying, he was asked, where do you see the future of computing? And he says, well, I see maybe the need of 5 or 6 computers in the world.
Yeah.
And then nowadays, we all know what will happen. So I don't want to be the guy who says something like that.
This other guy who said that we never need more than 640 kilobytes of RAM.
Exactly.
Right? It was this famous Mr. Gates.
Yeah, so we know where we're going, but we don't know where we're going to end up. And every time you have new people coming in the field, there's always new ideas, and it's a field that is growing extremely fast because there's a very large potential in the quantum world to do very nice tasks that we're not able to do nowadays. So the bottom line is we don't know how it's going to look like. We're not quite sure how we're going to do it, but we know that there's something out there, and we know the potential of it, and that's why we're pursuing all the research that we're.
Okay, I guess this is a nice summary. I have to say, we talked for about an hour or something, and obviously I don't get it completely. I did get a better feeling for where we are and how it's supposed to work, but it's a very abstract topic, and so I'm still. This is still quite a ways away from actually being able to explain it to somebody else, I guess.
Well, if you want to explain it in a very nutshell, here's what quantum information processing is.
Okay.
Our goal is to understand, harness, and control the quantum world to apply it to specific tasks that cannot be done or that is hard to do with today's technology.
That's a nice summary.
Yes.
Okay, then I thank you very much, Martin, for being on the show here.
Yes, thank you very much. That was very interesting.
Good. Thank you.
Okay,
Bye.
Thank you very much. Bye.
Bye. Thanks for listening to Software Engineering Radio. SE Radio is an educational program brought to you by Hillside Europe. If you want more information about the podcast and the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig, Reddit, Delicious and Slashdot buttons, or by talking about us on Twitter and Facebook. You can also support us by joining the team and shouldering some of the work. To contact the team, please send email to team@se-radio.net, or if your feedback is specific to an episode, please use the comments facility on the website so other people can react to your comments. This episode of SE Radio, as well as all other episodes, are licensed under a Creative Commons 2.5 license. Please see the website for details.